So good afternoon, everybody. And I'll request the chair just to alert me if I'm not audible.
I can.
So today I'm going to talk about Rashford systems. In particular, show you why spin textures are important for Rashford systems and how one can use theoretical ideas to tailor such spin textures hosted by Rashford systems. Well, so this work benefited from funding of SERB, so that which I like to acknowledge. And next, of course, this work was definitely not possible. I don't know why it's not moving. Definitely not possible if I didn't have the help of my graduate student, Shubhodip Bandopadhyay. In fact, he did most of the work, and he was also helped by Atanu Pal, my former graduate student. My former graduate student. Well, sorry about it. Well, so spin orbit coupling essentially brings in a new paradigm in quantum matter. And what is this? So for example, let us look at this figure. So this vertical axis is something with which we are all familiar with. And this is this axis where when the Coulomb interaction dominates the hopping. And this is the regime of 3D transition metals, and where we essentially have the traditional Mott insulators. And this is where the essential and this doping, this transitional Mott insulators results in the physics of high TC QMATs. Last 10 years ago or something like that, this axis where U is not that important, but spin orbit coupling is very important, came into prominence because of the discovery of the topological insulators, where because of spin orbit coupling, you have band inversion. And this is also a regime which also hosts, for example, the Rashford systems. Another interesting regime about which I'll not talk here is the regime where U by T and lambda by T are comparable, right? And this is this regime, if you go ahead and do a strong coupling expansion, you essentially get, in addition to the Heisenberg exchange, you also get a Kitaev exchange, which are bond-dependent exchange interactions. And that essentially gives rise to very interesting magnetic properties like quantum spin liquid states with gapped and gapless excitations. So today's talk will essentially concentrate on this regime, where the systems that I'm going to consider are weakly correlated, but have dominant spin orbit coupling. And the phenomena that I'm going to talk about is Rashford system. Well, so let's try to talk about a little bit about spin orbit coupled systems. As this slide shows, taken from this review, appearing in Nature Materials some 5 years back, that spin orbit coupled system holds a plethora of interesting property, which ranges from quantum spin Horn effect to topological insulators on one side, to several kind of device concepts, which include spin transistor, spin orbit qubits, spin orbit torque, and so on and so forth. To which tells us that it's indeed that spin orbit coupling brings in functionality, brings in new physics, right, which remained to be explored. And this talk will possibly address only some of these issues. Well, let's move forward. So what is Rashford effect? Well, so Rashford effect is momentum dependent splitting of bands in non-centrosymmetric systems. If you have a system which does not have inversion symmetry, then the band split, and how and why they split is something which I'm going to discuss. And this is essentially, this non-centrosymmetry can also be obtained if you apply an electric field. So this idea was essentially applied in the year 1990 to design what is known as Datta Das fate. So what you have here is a standard fate where the source is a ferromagnet and the collector, the drain, is also a ferromagnet. And in between you have a system which can host Rashford effect. So for example, what has happened when electrons for single spin are injected into the system, then Rashford effects acts into it. And what this Rashford effect does, Rashford effect essentially rotates the spin. And this rotation of the spin can now be controlled by an electric field. So this is an important thing, that you are able to control or you are able to manipulate spin with the help of an electric field, right? And this is essentially the key idea of spintronics, that you would like to manipulate spin applying an electric field, Rashford spin splitting has also been seen or discovered and manipulated in topological insulators. The surface states, right, when an electric field is applied or suitable gating is done, then one can clearly see that that this Rashford splitting, and which can of course be applied to variety of application. Well, with this little bit of application in mind, let us get back to the physics of Rashford. Or there's also another effect which is called Dresselhaus effect. The difference between Rashford and Dresselhaus effect will be clear as I move on. So what is Rashford effect? This is momentum dependent splitting of spin bands in a non-centrosymmetric or a system which does not host inversion symmetry. In such a system, you can have momentum dependent splitting of bands. So let us try to list the kind of symmetry that we usually have in a crystal. So we have this crystal symmetry, crystal inversion symmetry, which is EK up is equal to E minus K up. We have time reversal symmetry. And if both these symmetries are present, then we have so-called Cramer's degeneracy. Both the bands are degenerate, right? This is a standard thing. Well, so now what we can do, you can apply a magnetic field, or by some means you can go ahead and break the time reversal symmetry. And if you break the time reversal symmetry, then you go ahead and distinguish between an up and down spin band. And of course, this splitting is not a K-dependent splitting. And this is a splitting which you, for example, get when you do a spin polarized density functional calculation. Well, so you break the time reversal symmetry and you can split your up and down bands. What I'm going to talk here today is a totally different effect. If you have a system which breaks inversion symmetry, and let me also alert you that the inversion symmetry can be broken by applying an external electric field. And once you break this symmetry, then again the band splits. The upspin and the downspin band splits. They split in a slightly different way. Now the splitting is K-dependent, and they host a different kind of spin texture. And this is something which I'm going to talk about today, and which essentially distinguishes between the so-called Rashford effect and Dresselhaus effect. And the interesting thing is that now we're able to split the spins by applying an electric field, right? In contrast, what you normally do, you essentially split spins by applying a magnetic field. Well, so how this thing happens, right? So let us try to look at it. In absence of inversion symmetry, there is, of course, a potential gradient, right? From the positively charged nucleus, which generates an electric field, right? So if you break an inversion symmetry, there is a potential gradient, and which gives rise to an electric field, or otherwise you can even apply an external electric field. So when this is the case, this electron sees a magnetic field in its rest frame, right? And this is simple special theory of relativity. And this magnetic field now interacts with the electron spin, and this is very clearly shown here how it happens, right? So this is your relativistic field, and this is your spin, and this now gives rise to a kind of what is known as a spin orbit interaction, and this is what is known as a Rashford spin orbit interaction. Now, if you assume the electric field that is being applied or that is being produced is along the z direction, then you can essentially work out a Rashford Hamiltonian, and this Rashford Hamiltonian has this familiar form, right? And what we have achieved at the end of the day, the thing that we have achieved is electric field has been converted to a momentum dependent magnetic field, right? And this momentum dependent magnetic field, of course, will split the spin states. That's what we go ahead and see. Well, so this is what you can go ahead. So I just showed you the Rashford Hamiltonian. You can also derive by the symmetry consideration the Dresselhaus Hamiltonian. Rashford effect was originally invented in the context of surfaces and interfaces, while Dresselhaus effect was in fact invented in bulk systems which breaks inversion symmetry. And as you can see, the Hamiltonians are of course linear in K, but there is a slight difference. If you go ahead and work out their eigenvalues, right, they are absolutely identical. So what distinguishes between a Rashford effect and a Dresselhaus effect? The thing which distinguishes between a Rashford effect and Dresselhaus effect is the spin texture. So what is spin texture? Spin texture is you have to essentially calculate the expectation value of the spin operator Sx, Xy, and Sz, right? And this orientation of the expectation value of the spin operator is essentially the spin texture. So as you can see, the Rashford spin texture looks something like this, right? Which essentially rotates around the around the point in which I am interested in Rashford effect. On the contrary, you can see this is how the Dresselhaus spin textures looks like. And what people are interested in not only having the Rashford or Dresselhaus spin orbit interaction, but people are also interested in having a particular kind of spin texture in designing devices. So what this talk will do, this talk will possibly give you some insights by which you can think about understanding how you can control spin textures in these materials. Well, so with this, let me go to the next slide. And so this is what the general Hamiltonian is, which has been written by respecting symmetry. And this Hamiltonian, depending on the value of alpha and beta, can host either Rashford effect or Dresselhaus effect or both, right? So when as you can see, the Rashford parameter is nothing but alpha minus beta by 2. On the contrary, Dresselhaus parameter is nothing but alpha plus beta by 2. So what I have done, I have taken this Hamiltonian, and now I've taken these very special cases where alpha is equal to 0.5 and beta is equal to minus 0.5, where you have only alpha R and not alpha D. And as you can see that you have the standard Rashford spin texture. Well, so what is the next thing? Next thing I have chosen alpha to be 0.5 and beta to be 0.5. By this, I essentially suppress the Rashford term, and now you have this Dresselhaus spin texture. But what people are talking about today is what is known as persistent spin textures. The spin textures which are not dependent on the K values. And how you can generate that? So you can generate that either by choosing alpha equal to 1 or beta equal to 0, which implies that alpha R and alpha D, that means Rashford parameter and the Dresselhaus parameter, identical in magnitude and sign, or they are identical in magnitude or but different in sign. So why people are looking for this persistent spin texture? Because these persistent spin textures are robust against spin-dependent disorder, and this essentially gives rise to give essentially an infinite spin lifetime. So for example, when you're designing a device, there will obviously be some impurities and things, and as a consequence, the spin will lose its coherence and lifetime, and spin transport will not be possible. But if you can have a system, right, which can essentially sustain persistent spin texture, then you can essentially guarantee a very high lifetime through such spins, making spin transport a possibility and the performance of a device. So how to design such a persistent spin texture or persistent spin helixes, right? One, of course, is you design a material where your Rashford coefficient is equal to your Dresselhaus coefficient. And this is something which was suggested in 2017. People also designed a system, but of course, you know that controlling a Rashford parameter and Dresselhaus parameter is not difficult. Another idea had been that why don't you exploit symmetry? And this is something which I'm going to talk about today, that one can exploit symmetry of a given system, and then one can essentially predict whether you can have a Rashford effect or a Dresselhaus effect or a persistent spin helix or a persistent spin texture. So let's move on. So the next thing is that we have to search for Rashford systems, right? As I told you, the requirement for a Rashford system is what? Number one, absence of inversion symmetry, and these systems preferably should also be insulators, right? And the class of system which does that or which satisfies these properties are ferroelectric system. Ferroelectric system, by their design or by their nature, they are insulating, and they also does not have inversion symmetry. Otherwise, ferroelectric polarization cannot be done. And more interestingly, the ferroelectric polarization can be controlled by electric polarization. So if we can identify a ferroelectric system which can host Rashford Dresselhaus kind of spin orbit coupling, then we have essentially made a huge progress, because now we can essentially reverse the spin texture by an application of an electric field. And this is essentially one of the requirements of semiconductor spintronics, essentially controlling spin polarization by applying electric field in contrast to magnetic fields. Well, let's make slightly more progress. So the materials that we would be interested in are three materials I'll talk about today: this lanthanum tungsten nitride, bismuth indium oxide, and Ag2BiO3. Let me tell you, the only experimental synthesized compound is this BiINO3, lanthanum tungsten nitride, or Ag2BiO3. Ag2BiO3 has been experimentally synthesized, but nobody has measured its ferroelectric polarization. And lanthanum tungsten nitride has been predicted theoretically, and we have essentially shown that it sustains ferroelectric polarization. Why I have chosen this? I've chosen this for two reasons. That all these three compounds has the same space group symmetry, number one, and they also have non-symmorphic symmetry, which will be very important, because as I show you this non-symmorphic symmetry is standard point group symmetry coupled with some non-primitive translations, right? This is what makes it non-symmorphic. So as I told you that all these three systems belong to the point group C2V with a ferroelectric polarization along the 001 direction, which will make our theoretical analysis slightly simpler. And the magnitude of polarization theoretically calculated for lanthanum tungsten nitride is 20 microcoulomb per centimeter square, while it is 33.6 for BiINO3, which has been measured. And for Ag2BiO3, the predicted figure is 8.8. So let us first take this lanthanum tungsten nitride and try to understand what kind of, whether we really have. So it satisfies all the criteria. It is an insulating system, and let me tell you, it's a band insulator. So I don't have to put in Hubbard-U or anything of that kind. Just life is simple. Secondly, it's the ferroelectric, so it automatically breaks inversion symmetry. So I have all the necessary ingredients to host a Rashford Dresselhaus SAW. Well, so this is something we already talked about. So let's look at the band structure of the system. So this is what is shown here. So I will essentially be concentrating at the conduction band, which is built of, or which is essentially made of tungsten 5D states. So this is a calculation without spin orbit coupling, and this is the calculation with spin orbit coupling. And as I pointed out, that the electric field of the polarization in this case is along the Z direction. As a consequence, you don't see any splitting along this gamma Z direction, right? Once you apply your spin orbit coupling. Around gamma, there is some splitting, but this splitting is small. But along this Z point, and you can see this gamma point is of course center of the Brillouin zone. Sorry, and the Z point is out here, and there's a huge splitting around this Z point. And these can be either due to Rashford effect, or due to the Dresselhaus effect, or due to a combination of this thing. And this is something which you'd like to figure out. Right. But as I told you, since there is no splitting along the gamma Z direction, this is consistent with Rashford Dresselhaus effect. Well, so what we have to do, we have to essentially look at the point group symmetry, write down our Rashford Hamiltonian, write down our Dresselhaus Hamiltonian, and try to figure out whether Rashford term is allowed or the Dresselhaus term is allowed. And in this case, what we figure out, given the point group symmetry C2V, both the Rashford term as well as the Dresselhaus term is allowed. Well, so with this information, or with this group 3 exercise, let us go ahead and look at the band structure. So what we are doing, looking at the band structure around the gamma point in presence of spin orbit coupling, and we can clearly see that the band splits. And what we have done, we have now calculated the spin texture for the inner branch and the outer branch, as you can see. And the spin texture clearly tells us that although there's a possibility of both Rashford effect or a Dresselhaus effect, but the spin texture clearly tells us that this system essentially hosts Rashford effect, right? So we can essentially understand this in slightly more details. So let us go ahead and do that. So what we find, that the orientation of spin texture is opposite to each other, which implies the helicity is opposite. Out of plane spin component is absent. So there is no out of plane spin component, which is consistent with the Rashford effect. Rashford effect doesn't give you sigma Z is equal to 0 in the case of pure Rashford effect, and this is precisely what we see. Well, so we can do a little bit more exercise. That's what we have done. So what we have done, we have essentially written out this model Hamiltonian, right? And then what we have done, we have essentially figured out the Rashford parameter and the Dresselhaus parameter for this system, right? So this is our full DFT calculation, and this is our model calculation. So this is our full DFT band structure fitted with a model band structure, and the fit is excellent. And what we get at the end of the day, that for this system, Rashford coefficient dominates the Dresselhaus coefficient. So here, for example, Rashford effect dominates. So this essentially provides us a kind of an understanding. Well, so what we're essentially interested in, we're essentially interested in this huge splitting around the Z point. And the Z point is also very special. The Z point is very special. The reason being that here, for example, my non-symmorphic operations will play a role, right? So this is what, so I'll not get into the details. So what we can essentially go ahead and do, so now we are
5 more minutes. 5 more minutes are there.
Okay, good. Yeah. So around the Z point, we look at the band structure and we essentially look at the spin texture. And again, we find around the Z point, it is a Dresselhaus term, but with a caveat. Now the spin texture also has a Z component, right? You can see the spin texture now has a Z component. And this is because of non-symmorphic operations which comes into play here. One can go ahead and do the similar analysis and again prove that for this system, the Rashford effect dominates. Well, so with this thing, let's make some more progress, right? So what I've showed you, at least I've shown you that for this lanthanum tungsten nitride, right? If I look at the conduction band and concentrate at the Z point, the character of the band at the Z point is predominantly tungsten D x square minus y square. Once you apply a spin orbit coupling and look at the spin texture, then the spin texture is that of a Dresselhaus Rashford kind. Well, so let us move to this next compound. This is bismuth indium oxide. You can do a similar exercise. Again, look at the conduction band. That's what we look at. Now the conduction bands and the predominant bismuth px and indium s character, right? Again, a large splitting at the Z point, but out here you see the spin texture is that of a persistent spin helix or a persistent spin helix, which is something which people are looking for. Well, what is the case for the third compound? If I do the same thing for the third compound, now I figure out that the character of the bands is nothing but bismuth S and oxygen Pz. If I go ahead and analyze at the Z point, then I figure out this shows Dresselhaus spin texture. So you can see that all the compounds have same symmetry, right? But they host 3 different kinds of spin texture. And out of this, for example, bismuth indium oxide is the one which is more sought after because it essentially hosts so what we have obtained, so as I told you that for lanthanum tungsten nitride, we have Rashford. For bismuth indium oxide, we have persistent spin helix. On the contrary, for Ag2BiO3, we have Dresselhaus effect. All have the same point group. The space group for lanthanum and bismuth indium oxide are identical, but the space group for Ag2BiO3 is slightly different because of slightly different non-symmorphic operation. Well, one of the ideas that why they are going to hold so what essentially dictates spin texture is essentially symmetry. But what we find that lanthanum tungsten nitride and bismuth indium oxide having identical symmetry, right? Identical non-symmorphic symmetry and everything, right? They essentially host 2 different kinds of spin texture. So this is something we try to understand, and we figured out that the reason for this is that the main character of the bands at this particular point, and the Z point, is different from lanthanum tungsten nitride and bismuth indium oxide, and which plays a very crucial role in dictating the spin texture, which was not really understood before we essentially did our calculation. Well, I'll not get into the things. You can essentially work out the symmetry. So this is what the summary slide is. So if you take lanthanum tungsten oxide, the symmetry of the orbital, which happens to be here, tungsten D x square minus y square, allows all the spin operators, right? As a consequence, you can take the linear Hamiltonian in its full glory. On the contrary, for bismuth indium oxide, the orbital symmetry suppresses this sigma x, right? And similarly, absence of SZ symmetry suppresses the sigma z operator in Ag2BiO3. And once you essentially take this orbital degrees of freedom, or you do an orbital symmetry adapted K-dot model, then you can essentially go ahead and describe their different spin texture they host, which is, for example, Rashford, like for lanthanum tungsten nitride, it is persistent spin helix. For bismuth indium oxide, on the contrary, it is of Dresselhaus kind for Ag2BiO3. I think I have run out of my time. So as I told you, lanthanum tungsten nitride, when we did our calculus, this compound was only theoretically predicted. But by the end by the time when we finished our calculation, there was a report early January this year that somebody could synthesize this compound, but also it's in a slightly different phase, in a rhombohedral phase. And interestingly, this rhombohedral phase also shows very similar kind of property, which I did not discuss today. Well, this is the summary. So broken inversion symmetry with shock can produce linear K-dependent splitting of the bands, which I told plays a very important role. Value of Rashford splitting can be controlled by strength of spin-orbit coupling, strength of electric field induced by broken inversion symmetry, and this provides an opportunity of manipulation of spin by electric field. And most importantly, which I think was not understood in the literature, orbital symmetry is very important in deciding the nature of spin texture. With this, I thank you for your attention.
Thanks for the very nice talk. And now the talk is open for questions and answers. In the chat box, I don't say anything, but anybody can, yeah, I see something now. Yes, please, Professor Bate, yes.
Hi, thanks, Indra, for a nice talk. I have one question.
Yeah.
So, is there any analogous system in 2D where I can have an interplay like this of Dresselhaus and Rashpa, where I can get this persistent spin texture kind of thing? Or is it possible, at least in principle?
In principle, it should be possible. As I was trying to tell you, for example, 2D system by their definition will break inversion symmetry.
That's right.
Number one. Number two, now if we can essentially tailor proper orbitals, so now one has to essentially go ahead and look at the symmetry which is present in that 2D system. And if we can essentially identify an suitable operator which is essentially participating in the splitting, that which is the right kind of symmetry, I think you can possibly
okay, I understand.
Persistent spin helix. Yeah.
Okay, thank you. Thank you.
Welcome.
Hi, I have a question.
Yeah, please go ahead.
Hi, this is Shubhro. The question is that regarding the two kinds of spin textures that you showed around gamma point and Z point,
yeah,
are these two spin textures continuously deformable into each other?
No. So the symmetries are different. So so as I told you, this entire.
So what distinguishes between the two spin textures? Is there an invariant which distinguishes?
There is a variant which, let me just go back to a slide. I'll show you that there is a very important variant. I think it's a very good question. So this is around the, let me go. So this is around the gamma point. Okay, so this is around the gamma point. So the gamma point, so for example, the spin texture does not have sigma Z component.
Yeah.
It has only sigma X and sigma Y. Because, for example, here this non-symmorphic operations are not playing any role. So gamma point is essentially insensitive to these non-symmorphic operations. On the contrary, if you go to the Z point, so this red and yellow color is essentially out of plane and inside the plane component of the spin. So they start having this Z component, which is essentially shown here. So you can see, so it has sigma X, sigma Y, as well as sigma Z.
So what happens to the spin texture as you continuously go from the gamma point to the Z point? You expect this sudden jump in the nature of the spin texture?
I would guess so. This would be my guess, right? I mean, whether one can do it continuously. So my guess would be that possibly one cannot do it continuously.
I see. That's really interesting.
Right.
Okay, thanks.
Any other questions? Okay, maybe I have one fundamental question. In these Dresselhaus systems, is it possible to have 100% spin polarization?
Can you repeat the question once again?
In the Dresselhaus systems, spin splitting systems, is it possible to have 100% spin polarization at the Fermi level?
100% spin polarization?
Yeah.
Well, I mean, so these are, of course, so what you mean is that the system has to be a magnetic system, right?
Magnetic, yes.
Right. So in principle, magnetic systems, the point is the following. So I would like to preserve my time reversal invariance. So once you have a magnetic system, essentially breaks my time reversal invariance.
Okay.
So, right.
Okay, why I'm asking this question, because a couple of years ago, we published one paper on iridium bismuth selenide. There we showed like it shows 100% spin polarization.
But once you break your time reversal invariance, anyway, the bands will split.
Yeah.
So that you don't require any Rashpa effect or Dresselhaus or this kind of an effect. So here the business is that I would like to split bands by bringing in my electric field, right?
Yes, but that was our experimental study, RPES study, and
So
then
that's
the bands.
Uh, Can I just add a comment? So if you have a spin polarization, will this Rashba induced splitting be on top of the spin polarization induced splitting?
No, so the basic idea is that I would like to split bands applying an electric field. But once you already have broken your time reversal invariance, bands are already split. Now on top of it, if you would like to see Rashba effect or Dresselhaus effect, I don't think that would be of that importance.
Okay. So there are no more questions. I think on behalf of the audience, I thank you to Siddharth Gupta once again for the nice talk. Now we will move to the next speaker. So it will be, yeah. So
yeah, can you hear me? This is
I can hear you. Yes, Professor Maitra.
yes,
Tulika Maitra.
yes.
Yes, please.
Okay, so shall I share my screen?
Please share the screen. And she will be presenting the talk on non-collinear magnetism, spin phonon coupling, and orbital order in spinal vanadiums. Yeah, maybe presentation mode.
Yeah. Is it? Can you see it?
Yes, we can see and also we can hear your voice. Yeah.
Okay.
Please
Okay.
go ahead.
That is good. Okay. Okay. Good afternoon, everyone. First of all, I would like to thank the organizers for giving me this opportunity to present our work here. Today, I plan to discuss a non-collinear magnetism, orbital order, and spin phonon coupling in spinel vanadiates. So this is the outline of my talk. First, I will introduce the spin and orbital physics in vanadium spinel oxides. And then I will discuss the non-collinear magnetic order observed in three compounds, particularly manganese vanadate, FeV2O4, and CoV2O4. And we have done recently some density functional theory calculations with a newly developed exchange correlation functional, which is known as source-free exchange correlation functional. I'll present the results that we have got for these three compounds. And then I will also discuss the orbital order calculated from DFT calculations. And finally, I will discuss spin phonon coupling in manganese vanadate. So these, the work that I'm going to present are published in these references. So the spinel crystal structure or chemical formula is AB2O4, and the crystal structure is shown here. The A site is tetrahedrally coordinated by oxygen, and which are shown in blue here, and B sites are octahedrally coordinated by oxygen. And these B sites further form a pyrochlore lattice, which is a network of corner sharing tetrahedra, which as shown in this figure here. This is geometrically frustrated. That means if we have Ising spins sitting at these B sites having antiferromagnetic interaction, then all the interactions are not satisfied across all the bonds. So this structure is therefore geometrically frustrated. For us, this B site is the vanadium. Okay. So this vanadium is in 3+ valence state. So it has 2d electrons in an octahedral environment. So there are 2d electrons in the triplet degenerate T2g orbitals. So it is partially filled. Therefore, the orbital degree of freedom is not completely frozen. It's active, and the Wundt's coupling is also relatively strong here. So it is in the high spin state. So both spin and orbital degrees of freedom are active. So therefore, it gives rise to a possibility to have the spin orbit coupling playing a role here. So in these compounds, so spin degree of freedom is active, orbital is also active, and the lattice is geometrically frustrated. And because these are transition metal compounds, the Coulomb correlation is also expected to be high. So all these interplay of all these degree of freedom gives rise to very interesting structural and magnetic transitions which are seen in experiment. So I will discuss three categories of the spinel vanadates. One is, on the basis of this A site ion. So if A site is non-magnetic and orbitally inactive, like magnesium, zinc, or cadmium, there we see two transitions. One is structural and another is magnetic. For example, in zinc vanadate, we have a cubic to tetragonal structural transition at 51 Kelvin, which lifts partially the geometrical frustration, therefore gives way to the antiferromagnetic transition at a lower temperature at 40 Kelvin. Okay, so this antiferromagnetic transition, this antiferromagnetic order is a bit complex. Looks like this, where we have up down arrangement along xy direction, and up down in these two directions, xz and yz. But the vanadium moments, these are the vanadium moments shown here. The vanadium moments point along c axis, and but interestingly, the moment is much lower than theoretically expected for V3 plus state, which should be 2 mu b. This is much less than even 1 mu b here. Okay, so this is the class of compounds where the A site is non-magnetic and orbitally inactive. So then comes another class of compounds, which like MnV2O4, where A site is magnetic but orbitally inactive. So there we see one structural transition, cubic to tetragonal, but two magnetic transition, one from paramagnetic to ferrimagnetic, where manganese and vanadium spins are oppositely aligned, and then further lower temperature we see a non-collinear magnetic order, where the vanadium spins cant away from the manganese spins. Okay, so manganese spins are along c directions, whereas vanadium spins they cant away from c direction. So this results in a non-collinear magnetic order. And then the most interesting one is the FeV2O4, where A site is magnetic and orbitally active. So here we see 3 structural transitions and 2 magnetic transitions. So recently Kawaguchi and others, they experimentally derived this phase diagram, where you can see that there are multiple structural and magnetic transitions across, when you dope manganese with, in FeV2O4. Okay, so there are multiple structural and magnetic transitions observed in these compounds. So now coming to the non-collinear magnetic ground state, the neutron diffraction measurements predict non-collinear structure for FeV2O4 and also for COV2O4. A similar structure is predicted, which is called 2-in 2-out structure, where the vanadium spins, 2 of them point inward and 2 of them outward. This is the 2-in 2-out structure, non-collinear structure. Here we can see that the canting angle is as high as, over more than 50 degrees between manganese and iron and vanadium. And also the vanadium moment is much less than 1 mu b. In manganese vanadate case, the non-collinear order is not exactly 2-in 2-out, but it is something like this, as shown here. It's also determined by the neutron diffraction measurement. Okay, so the COV2O4 is one unique system where most of the experiments done so far could not determine any structural transition in this compound. So only 2 magnetic transitions are seen. One is from paramagnetic to collinear ferrimagnetic transition at 150 Kelvin. Another one is collinear ferrimagnetic to non-collinear ferrimagnetic structure. In non-collinear structure is also like FeV2O4, 2 in, 2 out here. So this happens at lower temperature, 75 Kelvin. Very recently, one report has where they have done high resolution neutron diffraction experiment on single crystals. They detected a very weak structural transition in this compound from cubic to tetragonal at around 95 Kelvin, but the C by A deviates from 1 by about 0.06% or something. It's very extremely weak structural transition was detected, and then further at lower temperature at T2, which is around 59 Kelvin, they say that there is a symmetry change, though it remains tetragonal, but symmetry goes from I4 by A1 and 2 I4 by AMD structure. Okay, so the symmetry changes at T2, which is 59 Kelvin. Okay, so in all these compounds, zinc vanadate, manganese vanadate, FeV2O4 and CoV2O4, what we see is the important thing that we see here is that the moment is much less than the expected 2 μb, which is expected from He3 plus state. So this is something not possible to explain by traditional DFT calculations, which predicted between 1.5 to 2 μb. In case of zinc vanadate, the spin orbit interaction is found to be high, giving rise to a high orbital moment, which was around minus 0.75 μb, which cancels partially the spin moment, therefore giving a small magnetic moment. But in the other compounds, MnV2O4 and FeV2O4, the X-ray magnetic circular dichroism measurements or DFT calculations indicate that the orbital moment here is not that high. It's very small actually. So the spin orbit coupling cannot be is not very dominant. So we will not be able to explain, like zinc vanadate, the low vanadium moment observed in these three compounds. So to address that, this low vanadium moment and the non-collinear magnetic order, we performed some calculation with a recently developed exchange correlation functional, which is known as Sourcefree exchange correlation functional. If we look at the Hamiltonian of the spin density functional theory, so the external potential can be written as a sum of this spinless or scalar potential plus the sigma dot b kind of term. Okay, so but this magnetic field which appears here is generally unconstrained. It's not necessarily to be represented by a curl of a vector potential. But the physical magnetic fields are not unconstrained, and these are given by del cross A, which makes this magnetic field source free. Okay, so but in this original Hamiltonian, this magnetic field is not source free. There is a source term or monopole term present. So recently in the source free exchange correlation functional, by solving this Poisson equation, they constructed this new exchange correlation magnetic field by this equation, and so which actually then becomes source free. So this BXC tilde, which is source free. So we wanted to see what is the how does it explain the magnetic properties of these spinel compounds, which are inherently non-collinear and the vanadium moments are low. So we performed calculations for all three compounds, and what we found is that this source-free exchange correlation potential calculations with U gives rise to a much lower vanadium moment than the traditional DFT functional, and it matches very well with the experiment for same U value for MnV2O4, FeV2O4, and COV2O4. So at U equal to 2.75, we see that it matches very well with the experimental moment. So it can capture the vanadium, low vanadium magnetic moment seen in experiment very well within this source-free exchange correlation functional. As well as the canting angle is also well reproduced, which matches very well with the experiment. Apart from the COV2O4, where it is a little larger than the experimentally observed value, but the trend comes out correctly that the canting angle reduces when you go from manganese to iron to cobalt. Okay, so not only that, we could also reproduce the correct spin texture or the non-collinear magnetic order that I talked about, which was seen in the experiments. This 2-in 2-out structure for FeV2O4 and COV2O4 are correctly reproduced in this source-free exchange correlation function, and also the manganese vanadate. So this actually gives a very good description within the DFT framework of these spinel vanadates, the non-collinear magnetic order of the spinel vanadates. We also looked at the, okay, so before going to the orbital order, I would like to discuss few interesting observations that we made. When we calculated the vanadium magnetic moment with respect to U and compared that with the traditional DFT exchange correlation potential like LSD plus U. So here we see that the vanadium moment increases with application of U, which is expected because the Hubbard U actually localizes the moment, so vanadium moment is supposed to increase with U. Whereas here, what we see is the opposite trend, which is counterintuitive, but we can understand this in the sense that the source term that was present in that magnetic field also increases with U, and when we remove that, then the vanadium moment reduces. Basically, what it does is that the vanadium moment is with higher U becomes more non-collinear, whereas if we do the traditional DFT calculation as a function of U, then what we see this with source curve, if you see that it drives the system towards more collinear, so the canting angle actually decreases with U, whereas the canting angle increases in this case. But this happens only when the spin is non-collinear or the moment is non-collinear. But for manganese moment, which is A site moment, which is collinear with the C axis, there the with source and source free both the functional behave similarly. So with U the moment increases, but here it is giving the opposite trend. So this is an interesting observation that we made while doing these calculations. So we also perform orbital order calculations for this non-collinear magnetic state, and what we see here is that these are this V1, V3, V4, V2, these four vanadiums. So this V1, V3 case, we see that this dxz orbital is predominantly occupied, whereas for V2, V4, the dyz orbital is predominantly occupied, both in MnV2O4 and FeV2O4. So this is more like a A-type orbital ordering, which where the dyz and dxz alternately occupied along when we move along C direction. And for COV2O4, we considered cubic phase here, so there is no orbital order seen. So this is what we get about the orbital order. in the non-collinear state or non-collinear magnetic order state in the spinel vanadates with the source-free exchange correlation function. So I would like to discuss a little bit more about the COV204, which so far, I mean, most of the experiments predicted that there is no structural transition here. So it is the electrons in this compound are more itinerant than in MnV204 or FeV204. So in fact, with application of moderate pressure, one can see that there is metal insulator transition in this compound COV204. So we had done earlier electronic structure calculation for this cubic phase of COV204, and what we found is that these two d electrons, one is localized in the A1G orbital because this phase is cubic. There is only trigonal distortion here in this compound. So the splitting is A1G and EG prime. So one electron is localized in the A1G orbital, and another one is delocalized over this EG prime, I mean doubly degenerate EG prime orbitals. So to explain this metal insulator transition, we had proposed this Kalikov-Kimball model with two itinerant band, and so where the hybridization between localized and itinerant state under pressure can lead to a correlated metallic state. This is what we explained earlier, but recently
5 minutes from now, 5 minutes are there.
Okay. So recently there was this experiment which showed that there is weak structural transition, and we also calculated because this will then lead to orbital order, and we showed that when the symmetry changes from tetragonal in the tetragonal phase, the orbital order also will change from ferro to A type, and with complex orbitals involved here and real ones here. Okay, so I think I'll just quickly go through this spin phonon coupling in MnV204. So this experiment was done by Gleason-Raman scattering experiment, where they identified the 1 magnon peaks and 2 magnon peaks in the antiferromagnetic phase. This 2 magnon peak is actually having seem to have anomalous temperature dependence. That means it is the energy is increasing when the temperature is also increased, which is unexpected because the spin-spin correlation should decrease, and therefore the energy also should decrease, like in this case. So this anomaly was attributed to spin phonon coupling. So we tried to model the spin phonon coupling in this system by considering this Heisenberg Hamiltonian, where this is between Mn and V spin antiferromagnetic exchange, and this is vanadium ferromagnetic exchange. And if we expand this exchange interaction due to spin phonon coupling as a Taylor series expansion, then it can be shown that the spins, frequency change in frequency or frequency shift due to this magnetic ordering can be shown to be equal to this J double prime, which is this second order coupling term here. And we calculated this shift in the phonon modes from our DFT calculation by done in two different magnetic orders, and we calculated this delta lambda, this shift, and then we did this Ginzburg-Landau theory, where we wrote down the free energy and the introduced this term which is due to the spin phonon coupling, and one can then calculate the new frequency due to the magnetic ordering, new phonon frequency. So from DFT we took this delta lambda and this magnetic order parameter. We considered a model which is given by this, with the critical exponent 0.5, which is mean field behavior, and the 3D Heisenberg behavior is given by beta equal to 0.365. We also considered experimental temperature dependence of magnetization, and for these three temperature dependence of magnetization with this delta calculated from DFT, we could explain the anomaly in the phonon frequency observed in that experiment, and it is seen to be originating from the softening of phonon modes due to spin phonon coupling at the zone center. So this is how we could explain through this Ginzburg-Landau theory the different temperature dependence of two phonon modes. One is at 70 centimeter inverse, and another is 178 centimeter inverse. Okay, so this is the summary. Non-collinear magnetic order and low vanadium moment values are correctly reproduced using DFT with source-free exchange correlation functional, and then anomalous temperature dependence of two Magnon peak in MnV204 was possible to explain by considering this spin phonon coupling. So I would like to acknowledge my collaborators, Jyoti Krishna and Dipendu De, who are at Arizona State University. Jyoti Krishna is my former student who is doing postdoc currently at Arizona State University. They are the ones who have done these calculations. And Sangeeta Sharma, Nisha Singh from Max Born Institute, Germany, J.K. Dewhurst and E.K.U. Gross from Max Planck Institute, Halle, and S. Alcross from University of Erlangen, Germany. So this we have done this source-free exchange correlation functional calculations with this German, in collaboration with this German group, and Umesh Wagmare from Jain Center and Orbital Order from IIT Kharagpur. We collaborated with them for this spin phonon coupling calculations in MnV204. So with this, I would like to thank all of you for your attention.
Professor Maitro, thank you for the nice talk. I see a couple of questions, one from Subro Bhattacharjee, other one from Bhaskaran. Professor Bhattacharjee, would you like to start the question?
Yeah, hi. This is Shubhro. So the question is regarding, most of the compounds that you told about, but to be specific, let's think about the zinc vanadate. What is the understanding that the structural transition and the spin transition are separate? Because if that is the case, then in the intermediate regime, on general symmetric grounds, I think you would expect a spin nematic state. So is there any signatures of that?
This actually structural transition, spin transition, this antiferromagnetic spin transition happens after the structural transition because, okay, so zinc vanadate, this one. So because this is this system, this pyroclue lattice is geometrically frustrated.
Yes.
So,
but once the structural transition happens, the frustration is lifted.
Yeah, but yeah, this frustration is lifted, then the magnetic transition follows.
Yeah,
so
but there is a separation of about 10 Kelvin.
In between. No, I don't know of any report of any nematic transition. Nematic state.
I see. Okay, thanks.
Professor Bhaskar, would you like to ask the question?
Yeah, nice talk, Tulika. I have a very short question about this very nice idea of source-free exchange correlation magnetic field. It looks like some Berry curvature magnetic field.
Yeah.
Are you putting spin orbit coupling, or it's arising without spin orbit coupling?
Yeah, we are putting spin orbit coupling. Yes.
Oh, you are putting spin orbit coupling.
Yeah.
And another question related to Subro's. So I'm wondering whether the structural transition also lifts the orbital degeneracy in zinc case, whether you have basically two of the orbitals occupied and the other goes up. Is it possible to see that?
Sorry, I couldn't hear your last part of your question.
I'm saying that in the case of zinc,
yeah,
below the structural transition,
yes.
So there is some octahedral distortion. So does it lift the orbital degeneracy, and you have basically spin one of the EG
orbital degeneracy is partially lifted. I mean, one electron goes to the XY orbital because there is a compression along C direction. But other electron still remains in a degenerate state.
I see. Okay. Thank you.
Okay, any other questions, please? Okay, if this is the case, then on behalf of the audience, let me thank Professor Maithra once again for the nice talk.
Thank you.
Then the next presentation will be given by Professor Mukul Kabir from IISER Pune. He will be talking on correct magnetic description of two-dimensional honeycomb chromium iodine 3.
So hello and good afternoon, everyone. So am I audible?
Yes, yes, we can hear.
Okay. So let me, for the sake of internet connectivity, let me switch off my video. And how do I do that? Yeah. So let me first thank the organizers for doing it online. And since they are doing an amazing job, I am afraid that things will be ever face to face again. So what I'll be discussing in this talk is I'll try to give a fairly complete magnetic description of two-dimensional honeycomb CRI3. Okay. And I will touch on some other related results around it. Also, let me thank the funding from various sources, including DST Nanomission, ACRB, and more recently, the National Supercomputing Mission. Without that, none of these calculations would have been possible. So first, let me give you a quick overview of what will be included in this talk. So first, I try to give you an experimental results, first couple of them that came out in 2017, and the understanding that led afterwards about this experiment. And then I'll speak about the journey of CRI3 from being thought about an Ising ferromagnet to an Heisenberg ferromagnet, and also related fine tuning of it. Okay. And then I will try to give you an idea that since the transition temperatures of these materials are much lower, is there a way to manipulate the TC in these materials? And at the end, I will very briefly and not describe, touch about a couple of interesting van der Waals heterostructure where these 2D ferromagnets serve as a substrate. And some of these calculations are done by two of my PhD students, Chandan and Deepak. So when it comes to 2D materials, and these days people talk about these van der Waals 2D magnets, one at the onset, one might ask the question that while there are many ferromagnets available with very high TC, then why just go ahead and thin it down these strongly magnetic materials doesn't serve our purpose to have a 2D magnet. The reason being such that you might already know that that thinning down a material will degrade its ordering temperature. Okay. But again, you might argue that since the ordering temperature at bulk is very, very high, it has a lot of room to go down. Okay. But in practice, that's not the case. For example, if you look into an example of elemental cobalt, that bulk TC is of the order of 1400 Kelvin. But once you thin it down to 1.8 monolayer to 1 layer, your TC quenches down to almost 25 Kelvin. So although you started with 1400 Kelvin in the bulk, you get a TC of 25 Kelvin in the thinnest limit. Okay, so that probably doesn't serve your purpose. On top of that, there are other various other difficulties that you will face. Is that there will be a very, very strong substrate dependency of this TC, because this thin layer of the material will chemically interact with your substrate, and whether your substrate is A or whether your substrate is B, depending on that, you will have a different TC, which may not always what you want. Another difficulty might be that, like, growing this thin layers might be not very controllable, and also retaining their crystal structure in the form that you want may be very difficult. Okay, so in this context, the magnetic van der Waals material might be an answer, which will also give you an handle that if you might have a magnetic material with much higher TC. Okay, so having discussed that, let us talk about magnetism in 2D in general. So the first order consensus that ordering is not possible following this celebrated Hohenberg-Markgreen-Wagner theorem. Okay. However, the continuous rotational symmetry of spins can be broken if you have a spin orbit coupling in the system, okay, which in turn gives rise to magnetic anisotropy. Okay, so that's one opportunity out of this theorem, which blocks ordering at 2D. Also, the magnetic interaction can be long range, which is beyond the requirement of this theorem of, like, where the sufficiently short range interaction was necessary. So in fact, if you think a little carefully here, then you would see that there is no clash between this theorem and having an ordering in 2D. Okay, and 3 years back in 2017, two such 2D magnetic materials were experimentally discovered. Both of them were chromium based. Both of them were in chromium based, and since then many other materials has also been discovered. Okay, but for our discussion, for our initial discussion, I will keep myself surrounded with this CRI3 and this CRGET, these two chromium based 2D materials. So let us take a closer look of these two experiments, and let us learn what these experimental results are telling us. So first, let us look into this CRGET material. Okay, you see that the car rotation is very, very, very tiny. Okay, and which is in the micro radian order. So that tells us that probably the magnetism here might be very, very fragile. Also, another very important thing which has been observed in this material is that the TC very strongly depends on the magnitude of the perpendicular field. Okay, and in some cases, if you don't have this magnetic field, it doesn't order. Okay, so so this dependence of TC with an external magnetic field rather unprecedented, which we haven't seen in 3D materials. Okay, so this is a very special thing in 2D, and this is probably telling us something which I will come in a minute. Then we look into the other material, which is CRI3, and I will mostly spend my time on this material later on. Okay. Similarly, with the previous material, the car rotation is also very small, but in milliradians now, which is like order of magnitude higher than the other material. Okay. And then it is also similarly observed that the external field strengthens your ferromagnetism. And again, your TC also depends on external magnetic field. So that put together, this TC and the external magnetic field business is actually telling us that the magnetic anisotropy in these systems are going to be extremely important. Okay, which we also otherwise have understood from Marmin-Wagner theorem, that if we do not have magnetic anisotropy, then you know, there will not be, there may not be any ordering in 2D. Okay. So what we have learned from these two materials about 2D is that they're quite different from what our understanding has been for 3D materials, that in 2D, that exchange interactions alone may not produce your magnetic order, A. B is your on-site anisotropy or what you call single line anisotropy will play a very, very important role. Okay, so that's coming out from the fact that the external field dependence of Curie temperature. Also, it tells us while this single line anisotropy is important, it also, this experiment is also telling us that the single line anisotropy in this material is very, very small. It is so small that that an off-axis magnetic field less than 1 Tesla will be enough to reorient your magnetic moment. Okay, so all this experimental understanding put together, one would understand that these materials are probably going to be an Heisenberg spin system rather than Ising one. Okay. On top of all this understanding that came out of experiment, we can also put one more understanding from our theoretical perspective, is that when you look into chromium and iodine, you see that there is a strong spin orbit coupling at iodine. So this chromium iodine bonding may also give rise to something called exchange anisotropy. Okay. So let us look into CRI3. So if you look into the crystal structure, the chromium actually gives rise to a in-plane honeycomb lattice, and the electronic structure is half-filled T2G and a completely empty EG. Okay, so this this electronic structure gives rise to a spin of 3/2, but at the same time, your orbital moment due to this half-filled T2G is completely quenched. Okay, And this chromium-chromium interaction is ferromagnetic. Now you know that this ferromagnetic superchange is rather weak, so you get a TC which is around 45 Kelvin. Okay. Now it would be important to note here that since your orbital moment is completely quenched, so the only possible quantum fluctuation in the orbital moment will give rise to a very, very tiny magnetic anisotropy. Okay, so from this electronic structure, we understand that that although there would be a single ion anisotropy at the chromium site, that's going to be very, very small. Okay, that one understands, and later on we will find out that calculation also gives the same picture. Okay. So then why it was initially thought that CRI3 is rather an Ising ferromagnet. Okay, and when you go back and read these two papers, you would probably understand that why they initially thought about it, because these two papers were being published at the same time in the same volume of the journal by collaborating groups, and they knew each other's experiment very well. So first let us look into this CRGTE. So where they found that there is no ordering in monolayer, but it orders from bilayer onwards. Okay, and the TC is much smaller than what they see as CRI3. So they thought that this material is a rather Heisenberg ferromagnet, and since CRI3 orders at monolayer and the TC is much higher than this material, so in comparison they put CRI3 as Ising ferromagnet. Okay, so that was the understanding at the time. Okay, so what we did, and like many others, okay, so we wrote down this Ising Hamiltonian by taking care of not only the first nearest neighbor, but looking into the complete like J1, J2, J3 Ising model. Okay, and calculated all these things, and then did a Monte Carlo simulation, and we find that if we take J1, J2, J3, then the TC is of the order of 140 Kelvin. Okay, which is much higher than the experimental TC. Okay, and I'll show you that there is a dependence of on-site Coulomb interaction, but these results are done with a very small u. So further increasing of u will increase your TC further. Basically,
sorry, Mukul, is there a typo in the Hamiltonian? You mean an Ising model, right?
Yeah.
And not a Heisenberg model.
No, not an
Okay.
Heisenberg model. Oh, sorry. This is the type. Yeah. This is an Ising model. Yeah. I will come to Heisenberg model later on. Okay. So this by this JK, I was showing that this would be J1, J2, J3. So all this 3, and this K is like first nearest neighbor, second nearest neighbor, or third nearest neighbor. Okay. So we were also checking that it gives us the Onsager's analytical result correctly, and if we have checked with the J1, where the Onsager's thing will give me around 92 Kelvin, my simulation gave as 93 Kelvin. So this is our test case for the code. So what we understand is that CRI3 is definitely not Ising. Also, without this calculation, we also have some understanding that why it should not be Ising. When you do calculations, you also see that it's definitely not Ising. Okay. So then, if you think a little away from your Ising model, you see that that your on-site anisotropy is very small. I'll show you the value in a minute. Okay, and not only that, as I has proposed earlier, that since your iodine has a very strong spin orbit coupling, there will also be some exchange anisotropy via these CRI bonds. Okay. Now, if you put these two things together, and if you write an anisotropic XYZ Heisenberg Hamiltonian, okay, where your Jx, Jy, and Zz is different, okay, along with the on-site anisotropy, okay. But you can also recast this XYZ Hamiltonian, assuming that you have this Jx equal to Jy, into this a little simpler form where your J1 now is some isotropic exchange interaction, and this K is something like this Kitaev-Taev exchange anisotropy along the Z direction, and you have this on-site anisotropy. However, I mean, there are many people who has used this this type of description for CRI3, but what we want to argue that this is also not a complete description for CRI3, because as I said, that exchange anisotropy is there, but there is only exchange anisotropy for the first nearest neighbor. Okay. So what we argue is that your J1 is not enough. So your first nearest neighbor interaction is not enough, and one must need to include the second and third nearest neighbor interactions. Otherwise, what would happen that you will not describe well the possible spin excitations. So in CRI3 alone, if I look into the ground state is definitely ferromagnetic, but my fast excited state is not the nil antiferromagnetic structure. Okay, and if you do not take, but it is not nil, but it is the zigzag antiferromagnetic structure. And if you do not take J2 and J3, you will never be able to describe the correct spin excitations here. Okay. So what we argue is that a rather complete description would be this model extended to your second nearest neighbor and third nearest neighbor. Okay. So that should be the complete description here. Okay. So now by putting it to some numbers, so we see that for CRI3, the ferromagnet is the ground state, and the fast excited state is the zigzag ground state, and the nil one, okay, if you only take J1, you would be only describing nil, is much higher in energy. Okay. And this ordering of spin excitations, I mean, the quantitative value might change, but the qualitative ordering remains invariant if you like describe your exchange correlation differently, or if you take a different value of Coulomb interaction, it doesn't matter. The qualitative ordering remains same. Okay.
You have 5 minutes.
Okay. 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 So now put some more numbers into it, and we see that the on-site anisotropy is very small, which is much less than 1 AVV. And if you put all these numbers into this Hamiltonian and do a Heisenberg classical Heisenberg Monte Carlo, then we find that the TC that we predict out of this model and these numbers are only 43 Kelvin, which is much closer to your 45 Kelvin that was experimentally predicted. If you take only J1, you would be much off to 29. If you take J1 plus J2 and not include J3, you would be predicting the TC to be much higher. So although the qualitative ordering does not change, we see that that increasing on-site Coulomb interaction increases your TC regardless what exchange correlation you take. And we believe that in this system, the U value is should be small, around 0.5 EV. And that is justified because due to this shallow p orbital of heavy ligand, your iodine strongly hybridizes with 3D, so you don't need a much bigger U to localize your 3D any longer. Okay, so now it would be interesting to see that whether we can manipulate the TC by some means, and we find that doping holes into this CRI3 is a very, very effective way to manipulate your TC, and we find that that only at about 0.5 holes per formula unit increases the TC by 5-fold to around 230 Kelvin, from 45 Kelvin to 230 Kelvin. Okay, and this is a kind of reasonable carrier doping, because we also know that, like, in materials like MOS2, already 5 times like 10 to the power 14 centimeter square type of, like, has been already achieved experimentally. So this is not something which is not experimentally doable. Okay, so this is within the limit. Okay, then when we dig a little deeper, then we see that, like, as we increase the hole density, your J1, J2, J3 has a strong variations and all these things, and you couldn't have done this thing with only J1. Okay, and the another important thing is that the anisotropic exchange interaction also varies very strongly with the hole density. Here also the important thing is that, to begin with, your J3 was antiferromagnetic, but as you dope more holes, it becomes ferromagnetic. So tentatively, one can explain these features in a way that for the neutral case, we already know from this Goodenough and Kogel-Komsky rules that, like, this interaction between the half field and empty EG orbital is ferromagnetic. But, like, when you dope hole, this dope hole at the T2G level also stabilizes ferromagnetism by destabilizing the antiferromagnetic interaction between the half field T2G and another half field T2G. Okay, so that is kind of qualitative argument for this these observations. We also observed that if we instead of doping hole, if we dope electrons, we see a completely different trend, and the TC goes down. And that probably comes from the fact that when you start populating this EG state, then your ferromagnetic T2G and the empty EG, which was otherwise ferromagnetic, gets suppressed. Okay. Also, one thing to notice here, that all this hole dope and this whitish electron doping regime, my spins were perpendicular to the surface along the Z direction. But if you go beyond certain electron doping and certain hole doping, your spins then lie in plane, and then your Hamiltonian, rather than XXZ model, should be an XY model. Okay. Then we also try to look into chemical doping, and why we took this path is that, so if you go down in the periodic table, you increase the spin orbit coupling, but you remain in the half field T2G limit. And if you go towards vanadium, then you go from a half field to you introduce a hole into this T2G level, which might increase your on-site anisotropy. However, what we see that none of these cases actually work pretty well. It doesn't. Although in both this direction for different reasons, this is for a hole into T2G level, and this is for increasing spin orbit coupling. What we find is that the on-site anisotropy increases, but your other parameters reorganizes in such a way that your TC doesn't help much. Okay, and as we also have,
we are running out of time. Could you please?
I'll finish it in maybe a couple of minutes. So we also have seen that once we dope hole into this W doped CRI3, that also doesn't help much, as it was rather helping in the pristine CRI3 case. I'd also briefly mention that when you are looking into chemically doped CRI3, the one limit would be by looking into VI3 rather. And there has been a recent experiment where they see a magnetic transition at around 50 Kelvin. And then there is a recent theory who proposes that it to be a two-dimensional Ising ferromagnet, and calculated TC was 75 Kelvin. But I wonder this result to be correct, because this is a single layer calculation, and where the TC is much higher than your bulk TC, which is a little suspicious result. Okay, because you expect your TC to go down rather, or remain same. Okay. So we put forward the similar model into VI3, and we find that on-site anisotropy is rather very small, and which is far below the Ising limit. And we also have strong exchange anisotropy, and the predicted TC is about 55 Kelvin, which is like similar to the bulk number. So we would rather propose this to be an anisotropic Heisenberg model rather than a Ising ferromagnet. I will take one more minute and I'll finish it. So another interesting fact for CRI3 would be it can serve as a substrate for various exotic other 2D materials, just like RuCl3, which is a quantum spin liquid candidate. And if you look into this RuCl3, you see that the zigzag antiferromagnetic ground state is almost degenerate with the ferromagnetic excitation, whereas the stripy and nil is little higher. But all these energy scales are order of magnitude lower than the energy scales that we have seen for CRI3. Okay, so you expect that something going to happen if you place CRI3. You place RuCl3 on CRI3, and we find that due to this ferromagnetic proximity influence, this RuCl3 becomes ferromagnetic. Okay, it would be very interesting to see that what happens to the spin excitations, which we are currently looking into. The last thing I want to say is that another heterostructure which might be very interesting is a superconductor ferromagnet interface, and for that we have looked into this NBSE2. NBSE, sorry, I have. So I have chosen NBSE2, which is an Ising pairing. Here the question one needs to ask that what happens to the superconductivity, and we find that when the CR moments are perpendicular and in plane, in both the cases, due to proximate exchange splitting, NB gains a moment. But what happens to the superconductivity? Is it suppressed, or you get a topological superconductivity here? Needs to be investigated. Okay, so what we have understood from here is that which model fits the experimental results should be very carefully dealt with in these 2D materials, whether it is Icing or Heisenberg. You need to look into various anisotropies. You also need to be very careful that how many nearest neighbor interactions are necessary. Although the TC is low, there might be ways to manipulate them to achieve room temperature magnetism in these materials. And lastly, the designer heterostructures may have enormous possibilities in otherwise inaccessible physics in this 2D materials. And thank you for your attention.
Yeah, thank you. Actually, we have taken more than discussion time also. So
okay.
there's no
Sorry.
time for discussion. But anyway, I see that. Thank you for the nice talk. So I see 3 people are asking the questions from the chat box. One is Professor Tanushree Dasgupta, Professor Indra Dasgupta, and Professor Subhroj Bhattacharjee. Could you please go one after another quickly? Maybe first Professor Tanushree Dasgupta.
Mukul?
Yes.
I think I would like to point out for this chromium, germanium, tellurium.
Yes.
There actually the spin-orbit coupling is weak, and
yes.
The anisotropy, single ion anisotropy is weak.
Yes.
But the experiment as well as the theory was done in presence of moderate magnetic field.
Yes.
And
yes.
that helps in kind of acting as an effective spin orbit.
Yes, yes, yes.
And that stabilizes the order.
Yes.
Although experimentally they said they could only do up to bilayer,
yes.
but calculation shows it goes even to monolayer, very much like chromium triiodide, although the transition temperature is not very high.
Yeah.
But here the origin is the single ion anisotrope.
Oh, yes, absolutely. You're right. I mean, that is what I was pointing here, showing that, like, your TC in fact depends on the magnetic field, and this result is for 3-layer, but they didn't get an ordering for single layer. Yeah.
Yeah, but
okay.
theoretically
Sorry, we have to move on. I'm sorry. Yeah. The next question, please, from Professor Dasgupta, Indra Dasgupta. It would be great if it is short question. It's not there.
I think he has to unmute. Is he unmute?
Oh, yes, unmute.
Yeah.
I don't.
Mukul, can you hear me?
Yes, I can hear you.
Please.
Yeah, good. So the thing is that you have gone till second nearest neighbor or third nearest neighbor in exchange interaction. What about DM interaction?
So we haven't looked into the DM interaction as of yet, and there are few papers which argue that there is no DM interaction.
No, it has to be DM. DM interaction has to be there in second nearest neighbor.
So I know.
Okay. Anyway, since the time is short, we can discuss. Another quick question is that what is the sign of your Kitaev exchange?
Sorry.
What is the sign of your Kitaev exchange?
A sign of the Kitaev exchange.
Ferromagnetic or antiferromagnetic?
It varies actually. So it is mostly ferromagnetic. Okay.
Ferromagnetic. Okay. Good. Thank you.
Yeah. So, but it changes sign also depending on your hole density.
Okay.
Okay. Last question by Professor Bhattacharjee. Would you like to ask?
Hi, Mukul. I'm a bit confused. Maybe I missed something. Can we go to the Hamiltonian? It seems that the Hamiltonian has a O2 symmetry. So are you talking about actually XY type of transitions, the BTK transitions, when you talk about transitions? Can you open the Hamiltonian?
This one you mean?
Yeah, this seems to have a XY symmetry. So when you say transitions, do you mean BTK transitions?
No. It is not BTK transition, because if I let's say so if I make dz equal to 0, okay, then my spin will fall in plane. Okay, but if I make this dz also increase and then the TC will also increase linearly with this on-site anisotropy. Okay, so there is an anisotropic term here. Okay,
I see. So it's an easy axis anisotropy.
It's an easy axis anisotropy, exactly. So dz is along z axis. That is
yes. Okay.
Yeah,
but it's still positive.
Yeah. Shall we wind up?
Yeah.
Or
So positive means
are
like
there any more quick?
so in this, so one clarification, Shubhro. So this, like, in this Hamiltonian, okay, so if dz is positive, that means my spin is pointing perpendicular to the surface, to the plane.
That's an
Okay?
XY spin.
No, perpendicular to the surface, not in plane.
Okay, maybe we should discuss this offline.
Yeah, that would be great.
Okay, sure.
Okay, thanks once again for the nice talk. Yeah, I'm saying this on behalf of the audience. The next talk would be given by Saheli Samantha from SNB NCBS SN Bose. It will be 15 minutes talk. So she will be giving talk on influence of simultaneous iron and cobalt on magnetic and magnetocaloric effect in all D metal Heusler alloys. Can I see her here? I don't see her.
Yes, sir, I can hear you.
You are here. Okay, please share your slide. So I will be reminding you after 13 minutes. Okay, you can.
Okay, sir.
You can start, but I don't see the slide.
Sir, share option is not visible.
It should be there at the bottom, middle, green button, something like that. Share screen.
Saheli,
At the bottom.
first, okay.
Yeah, my screen is visible.
Yes, now we can see. Yes.
Okay.
Go to presentation mode, then it should be okay. So you have the time 13 plus 2. So make it like within 13 minutes.
Yes, sir. May I start? Hello?
Yeah. Yes, go ahead.
Okay, sir. Good afternoon. First of all, I'd like to thank the organizers for giving me the opportunity to present our research work. My presentation topic is the influence of simultaneous iron and cobalt doping on magnetic and magnetocaloric properties in all the metal Heusler alloys. These are the outline of my topic. First, I will have the introduction about magnetocaloric effect briefly, and its importance for practical application and relative issues. And I will also explain our experimental results and conclusion. It is known the magnetocaloric effect is a magnetothermodynamic phenomena that is basically the change in the temperature of a magnetic material during magnetization and demagnetization when the magnetic material is placed in an external magnetic field. So this MC is characterized by isothermal magnetic entropy change and adiabatic temperature change. Here I have shown the total entropy of a magnetic material when the magnetic field is absent. As we know, total entropy of a magnetic material is a combination of magnetic, lattice and electronic entropy. Now I am explaining how these two quantity can be measured from this entropy state function. So now when the sample is placed in an external magnetic field under adiabatic condition, due to the alignment of the spin, its magnetic entropy decreases. But the process is adiabatic, that means there is no heat release or absorbed into the system, so total entropy remains constant. So to compensate this decrease in entropy, lattice entropy increases and thereby the result increase in temperature of that material. So from this we can measure adiabatic temperature change at the same entropy, and also isothermal magnetic entropy is measured from the two different curves at the same temperature. So why we study this magnetocaloric effect? So the reason is the magnetic refrigerator that works on the principle of magnetocaloric effect. As it is known, magnetic refrigerator is considered as an alternative cooling technology of conventional vapor refrigerator because of its several advantages. First of all, it doesn't contain any harmful gases like chlorofluorocarbon, hydrochlorofluorocarbon, whereas the vapor compressor refrigerator causes global warming. And it is environment friendly, highly efficiency cooling technology. And another interesting point, it is energetically 30% more efficient than vapor compressor refrigerator. Therefore, from the application point of view, it is necessary to find such material with large MCA in a wide temperature range for application purpose. So to get the large MC, sorry, we should follow certain criteria. For application purpose of MC at room temperature, the TC of the material should be very close to the ambient temperature. If we see the from Curie-Weiss's law, we can measure both del SM and del T additivity. Here, this term is the denominator. Second, the specific heat of that material should be very low so that its temperature can be changed easily. And third, large del M by del T as it is proportional to the large MC. So from the last 4 decades, various types of magnetic material have been found in broad research area. So among the most promising material, nickel manganese based Hostler alloy have drawn attractive attention due to their multifunctional properties for commercial application. These are the formula of the full Hostler alloy, where X and Y are the transition metals and Z is the main group P element, and here I have given an example of Hostler alloy. First, we know Hostler structure is a cubic structure L21. Here, 4 interpenetrating FCC sharp lattices are present, where the X, Y and Z position I have already mentioned. Second, the Hostler alloy shows a separated structural as well as magnetic transition. And the structural transition is the diffusionless, that is martensitic transition. And we know structural transition is the first order phase transition, then that is not ideally discontinuous. So across this transition, we get a magnetization change, and therefore we expect to get large MC as del SM is proportional to the derivative of the magnetization. Also, we can easily tune this temperature, which is very effective for room temperature application. Third, as the Hostler alloy containing the transition metals are very low cost compared to the other rare earth based alloy. But the drawback of this Hostler alloy is the presence of the thermal as well as magnetic hysteresis that loses the net refrigerant capacity of that material, and also its brittleness property that limits its application. So to overcome this problem, we have chosen all transition metal Hostler alloy, as it is also cubic structure, and it also shows a couple structural and magnetic transition. As it contains all transition metals, so it is low expensive, and to reduce the hysteresis, chemical composition is widely used. So we expect this material would have very low hysteresis, and one interesting property of this material is the mechanical stability. As the reversibility depends on the mechanical stability, we should remember during thermodynamic cycle, the materials don't break. Therefore, we expect that this alloy would be promising candidate for the commercial purpose. So in the present work, nickel manganese titanium is our parent alloy, and this alloy is antiferromagnetic itself, and its transition temperature is nearly 600 Kelvin. So in order to tune the transition temperature of the room temperature and the turn antiferromagnetic to ferromagnetic state, we have substituted iron and cobalt simultaneous in the nickel side. Here the figure displays room temperature XRD data for all the samples. Here present 2 phases are present. First one is the cubic austenite structure, which is the cubic structure, and martensitic phase, which is the monoclinic structure. And the coexistence of these 2 phases that indicates that the structural transition may reside near room temperature. Here I have also compared with DSC result. DSC result shows the heat flow for all the sample across their structural transition, and all sample exhibit first order structural transition as the hysteresis is present between the endothermic and exothermic peak. So, and if we see in this figure, with increasing iron and cobalt, the transition temperature gradually shifted to the lower temperature. So after that, we focus particularly X equal to 18 sample as its transition temperature resides near room temperature, and hysteresis is nearly 9 Kelvin lower than the other sample. So combining XRT and DSC result, we conclude that iron and cobalt substitution efficiently decreases transition temperature. That means the parent phase is stabilized. Here I have shown the temperature dependent magnetization for all the samples under 500 watt state magnetic field within temperature region 80 Kelvin to 400 Kelvin. Here we have used two protocols, ZFC, zero field cooling and field cooling. By following ZFC, a martensitic to austenite phase transition is observed within 315 to 245 Kelvin. And this result shows that due to the cobalt and iron substitution for nickel, magnetization of the higher temperature austenite phase gets significantly enhanced, whereas the low temperature martensitic phase is very minimum. Before going into details, the reason behind it, first I come in this graph. This is temperature dependence resistivity under zero magnetic field. This was done in standard collinear 4-probe geometry from 300 to 3 Kelvin. If you see in this graph, there is abnormal change in resistivity during forward and reverse transition. And the resistivity in the martensitic phase is around 1.5 times larger than the parent phase. That means the lattice distortion in the martensitic phase is more disordered than the parent phase, and on the other hand, with increasing iron and cobalt content, the resistivity decreases. That means iron and cobalt weakens the lattice distortion. Now, if I compare with empty data, the magnetization increases with iron and cobalt. The reason is the iron and cobalt acts as a ferromagnetic activator. It turns the manganese antiparallel moment into the field direction. So that's why the TC gradually shifted to the higher temperature that indicates the strengthening of the ferromagnetic exchange interaction. So comparing MT and rho T curve, we have preciously measured transition temperature. After that, the magnetic isotherm has been measured with the temperature loop process under 3 Kelvin interval. Here, the parent phase exhibits the ferromagnetic behavior. On the other hand, magnetization is very low in the martensitic phase. But for X equal to 20 sample, here martensitic phase shows a high magnetization because here the iron cobalt content dominate the antiferromagnetic coupling. So using Amy's curve and also using Maxwell equation, we have obtained isothermal magnetic entropy change for 18 and 16 sample, and we got at 296 Kelvin a maximum DLSM value around 3.67 joule per kg per Kelvin, and is obtained for 1.4 Tesla, and also for 16 samples 2.38 joule per kg per Kelvin obtained at 315 Kelvin. So for application purpose, relative cooling power is an important parameter. It is basically the amount of heat that can be transferred between the cold and hot reservoir in one thermodynamic cycle. So relative cooling power is numerically obtained by simply multiplying the peak value of the del Sn into temperature window of full width at half maximum. And we got a very high result for 18 sample, is around 55.39 joule per kg, and also for a 16 sample 49.39 joule per kg. So here I have compared our result with other Hostler alloy, and our sample shows a high result compared to the other sample. So in conclude, the effect of the varying iron and cobalt with same ratio in nickel side on the crystal structure, thermal, transport and magnetocaloric properties have been investigated in all the metal Hostler alloys. And next, that working temperature of the present alloy can easily tuned for refrigeration and heat pump application. And the low field large MC that is associated with large relative cooling power that can make this alloy very promising as refrigerant material. Thank you for kind attention.
Shahil, thanks for the nice talk. I don't see any questions from the chat box. Are there any questions, please? Okay, let me ask you one technical question. In your XRD, I see broad peaks. Are these nanoparticles?
No, sir. This is alloy.
It's alloy. Then why the peaks are not sharp? Usually XRD peak should be sharper, isn't it?
Sorry?
For bulk, XRD peaks should be sharper. The peak's very broad, isn't it? What was the reason for having broad peaks?
Actually, here three phases. Actually, in this peak, high martensitic phase and austenite phase are mixed here. If I zoom it, then clearly observe all very here more than peak is there.
Okay. So, okay, thanks. So I see one question from Krishnakant Dubey. Please go ahead.
Okay.
No. Krishnakant Dubey.
Sir, am I audible, sir?
Yes, now I can hear.
Sir, ma'am, actually, my question is in your slide that in your sample, basically, by doping Fe and CO, it is increasing the TM.
Increasing, not decreasing TM.
Decreasing
temperature.
Okay, means what is basically Fe and CO doing there in decreasing TM?
Okay, when we dope iron and cobalt simultaneously in the nickel side, the iron and cobalt basically acts as a strong ferromagnetic activator. So this turns a manganese antiparallel moment into the field direction. So that's why we got a broad region of ferromagnetic here. If you see, in this graph,
can you make it shorter because we're running out of time?
So TM gradually shifted and ferromagnetic region is broader and TC gradually shifted high temperature.
Okay.
Yeah, I think we should wind up now. Sahili, thank you once again for the nice talk. So now the next presentation will be given by Shreya Das, again from SN Bose, and she will be talking on understanding the curious magnetic state of strontium-3 osmium-06.
Hello?
Yes, yeah, please share your.
Okay. Can you see, sir?
Yes, we can see the slides. Also, we can hear your voice. Please go ahead.
That's fine. Okay. So good afternoon, everyone. Myself Shreya Das. Today I'll be talking about our recent work that's titled as Understanding the Curious Magnetic State of SFT-OS-06. This work has been carried out under the supervision of Professor Tanushree Shah in collaboration with.
Yeah, we cannot hear you well.
Hello.
Your voice is very clear.
Is it okay now?
Be louder. Maybe you put your mic close to your mouth. Maybe that would help.
Yes, I'm holding it closer. Okay.
Oh, okay.
Now it's okay.
You have to just talk louder.
Okay. So this work has been carried out under the supervision of Professor Tanushree Shah in collaboration with Anita Hardar, Abhishek Chakraborty and Professor Indra Dashgupta. Here's the motivation of our work. Basically, the highest TC with the value 1060K ferromagnetic insulator double perovskite is reported in literature, and it is SF3OS06. Two allied compounds, SF2CaOS06 and C3OS06, are also reported in literature. So here few questions arise. One is, most of the ferromagnets are known to be metal, not insulator. And SF3OS06 is containing a 5D transition metal OS, not containing any 3D transition metal. But high TC is a property of 3D transition metal containing compounds rather than 5D transition metal containing compounds. So in this work, we are interested to find out the reason behind its high TC and explore the unusual ferromagnetic insulating nature of it. The above three mentioned double peroxides have general chemical formula A2B B prime O6, where A side can be strontium or calcium, B side also can be strontium or calcium, and B prime side is always osmium. If you look at the periodic table and go downwards along the row, we get that the electronegative Coulomb correlation decreases, whereas the spin orbit coupling lambda increases. So osmium is having such a position in periodic table that it will show the interplay of both U and SSU. Next, here is the brief description about double peroxide. Peroxides are having formula AbO3, where BO6 octahedra are corner sharing and making the interstitial bursts where A side cation sits in. And in double peroxide, as if we are doubling the peroxide formula, so it takes the form A to B, B prime O6, where B and B prime are the two transition metals. Here also BO6 and B prime O6 are corner sharing octahedra, and A side cation sits into the interstitial void. Due to the presence of two types of transition metal, double peroxides are having interesting properties and their properties are tunable. Next, the distortion in double peroxide and tolerance factor. We have in peroxide the ionic size mismatch of A, B, and O, and that the ionic size mismatch is described by Goldsmith tolerance factor T with the formula this where Ra is the anicodii of A, Rb is the anicodii of B, and Ro is the anicodii of O. In the same wise, in double peroxide, the ionic size mismatch is also described by this T factor, where we take the average of anicodii of B and B prime cations. For ideal case, T is equal to 1 and BO B prime angle is 180 degree. For T less than 1, that implies that the smaller A size cation and the peroxide compensate the size mismatch by tilting the BO6 and B prime O6 octahedra, and in the distorted case, the BO B prime angle deviates from ideal 180 degree. Here's the background studies. For SN3OS O6, we get it is ferromagnetic insulator with high TC 1060K. The structure is cubic and it's epitaxially grown on SRTiO3 substrate. Tolerance factor is 0.887. For SF2CaOS O6, this compound is having space group FN3F, that is cubic. Its tolerance factor is 0.924 and no description of its electronic and magnetic behavior is still present. For CH3OS O6, it is prepared in single crystals under high pressure condition. XRD data shows that it will have monoclinic structure. Its tolerance factor is 0.89 and its semiconductor ordering temperature is 50 K. So from these background studies, it is evident that SR3OS O6 is ferromagnetic insulator with high TC in cubic structure, whereas CH3OS O6 is monoclinic with lower transition temperature and antiferromagnetic. So it gives a hint that the crystal structure plays a very important role. So to carry our calculation, we have carried out density function and theory based calculation to get the ground state properties. Next, the crystal structure of C3OS O6. We already have the reported tolerance factor 0.887 and with the space group HO3. And the literature shows that triclinic and monoclinic are colloidal structures under high pressure synthesis in powder form. Another report by Vasala, where we get the percentage of compounds with different space group in this state as a function of tolerance factor, and this particular T value for he may see in this region, which shows us monoclinic structure also possible. To come over all the controversies, we have applied a genetic algorithm implemented in two specs to predict the actual crystal structure of SF3OS O6 theoretically in more accurate manner. And this applied to this technique, we get that monoclinic and triclinic are the most probable structures for SF3OS O6. So this is the cubic structure of it, which is already reported, and this is the triclinic structure, and this is the monoclinic structure what we get from our spec study. Next, to investigate this crystal structure, this matter in more detail, we did structural stability calculation, cubic versus monoclinic versus triclinic. To do so, we did an exercise for total energy E versus volume calculation in GGA plus SOC plus U scheme. In this figure, the black shows represents for the monoclinic one, green is for triclinic, and red is for the cubic structure. From this diagram, we can see that the energetics of triclinic and monoclinic are almost same. Though the triclinic one differs from the monoclinic structure by an energy difference 30 MeV per formula unit at the equilibrium volume. And the highest energy cubic structure differs from the lowest energy monoclinic structures by an energy difference 1.1 eV per formula unit. And 6.5% tensile strain is required to make the crossover between highest energy cubic structure and lowest energy monoclinic structure. So from this calculation, we can argue that monoclinic structure is the most stable structure of exactly OS 6. However, its reported stabilization in cubic phase is only due to the epitaxial growth of it on SFTI 3 substrate. Next, we have applied into the unfolding method calculation to get the on-site energies and hopping parameters. In this method, we have integrated out the degrees of freedom of strontium and oxygen and kept only the osmium D degrees of freedom to make the low energy Fuban Hamiltonian. And from that, we want to get the on-site energy and hopping parameters. Next, the instant interaction and hopping procedures. The nominal valence of osmium is 6 plus in SFQOS 06. That is, it is in 5D2 state. And OS is having an octahedral coordination with oxygen, which splits the 5D levels into T2G and EG levels. Due to D2 occupancy, two of the three T2G levels are occupied, one remains empty. And EG levels are separated by 4 EV energy difference from the T2G levels. So we can say that no hopping procedure is involved with EG. This case is for cubic, but due to monoclinicity, the T2G levels becomes non-degenerate in the monoclinic structure. So if we look into the hopping process involved, we see that there are two types of hopping processes. One is antiferromagnetic, another is ferromagnetic. In antiferromagnetic channels, virtual hopping takes place from half-filled T2G to another half-filled T2G orbital of two OS sites. Whereas in the ferromagnetic channel, virtual hopping takes place from half-filled T2G to empty T2G orbital of two OS sites. So our resultant exchange interaction becomes determined by the competition between these two process, antiferromagnetic and ferromagnetic. So here's a schematic representation of hopping procedures here for cubic and monoclinic. Next, to understand the role of crystal symmetry on magnetism, we have plotted the one-year function overlap here for both cubic and monoclinic structure. In monoclinic structure, the octahedra experience in-plane rotation and out-plane tilt. So for this structural deviation, the OSOOS angle deviates from across the face of the cube, deviates from ideal 90 degree, and along the edge of the cube, the strontium BOOS angle deviates from ideal 180 degree. In the both structures, the nearest neighbor hopping is denoted by T, and the next nearest neighbor hopping is denoted by T prime. So the one-year function overlap gives a remarkable trend here, where we get that for the cubic one, the OP-like bending of osmium T2G orbitals towards the A side strontium makes a well-defined connected path between two osmium sites across the face of the cube, whereas this overlap becomes misaligned for the case of monoclinic due to the structural deviation, as OS angle deviates from 90 degree across the face of the cube. And for the next nearest neighbor, due to the OP-like bending, same as we are having hardly having any overlap between the two OS sides, separated by T prime hopping path. Next, to understand the interplay between nearest neighbor hopping interaction T, crystal phase splitting, Coulomb interaction, Wundt's exchange, and spin orbit coupling, we have constructed a two-site model Hamiltonian which takes this form, where each on-site is the energy, with the on-site energies of OS T2G orbitals. For cubic structure, these are degenerate, but for monoclinic, these are non-degenerate. Each interaction incorporates all the effects of intra-orbital Coulomb correlation U, interorbital Coulomb correlation U prime, and Wundt's coupling JH. HSO gives the spin orbit coupling interaction, SOC which is defined as the SOC strength lambda, and HT gives the intersite hopping T between T2G orbitals. Now we applied exact diagonalization technique onto this model Hamiltonian to explore the parameter space more accurately, and obtaining the eigenvectors and eigenvalues will get the physical properties. Next, the transition temperature and phase space of SO3OS06. Here, the exchange interaction is determined by the energy difference of ferro and antiferro alignment of OS peaks for both the case cubic and monoclinic. Here, we have kept the U value at 2 eV and lambda value 0.1 eV and varying the JH value. We get these two diagrams. For the cubic one, what we see that the antiferro to ferromagnetic interaction and gets stabilized over the JH value at around 0.27 eV, whereas for monoclinic one it becomes 0.6 eV. So at the JH value 0.6 eV, we can see that ferromagnetic alignment of OS pins are favored in cubic state, whereas for monoclinic one antiferromagnetic alignment is favored. And if we look at the energy gain value at JH 0.6, we can see that at cubic this is around 30 MeV, whereas for monoclinic this is around 1.15 MeV. So putting the energy gain value in the midfield temperature, we get TC value for cubic is around 1300 K, whereas for transition temperature for monoclinic is 70 K. So from this diagram, we can argue that ferromagnetic state supports a large TC, whereas antiferromagnetic state supports low transition temperature. Next, we did the same exercise to get the UJH phase space. Here we did it for lambda equal to 2 eV and another is for 0.4 eV. The both JH phase space are qualitatively safe, only increasing of the lambda value shifts the antiferromagnetic ferromagnetic transition to a larger JH value as lambda favors antiferromagnetism. And we can see in the phase space that monoclinic, the ferromagnetic interaction is having a very tiny portion for the monoclinic structure, whereas in cubic structure there is a significant portion of ferromagnetic interaction. So from this phase diagram, we can argue that FM interaction is stabilized in monoclinic structure, whereas ferromagnetic is supported by cubic structure. The infect shows the orbital ordering of two TTG orbital of the four OA sides of XCC of the tetrahedra, and for the stabilized ferromagnetic state, and as the ferromagnetic interaction is from hopping from filled T2G orbital to empty T2G orbital. So if we look at the connecting vectors along 110 and 011 and 101, the hopping is between filled to empty dxy, dyz and dxj orbital respectively. Next, the electronic and band structure of cubic SF3OS06. Here we have uncovered the insulating nature of ferromagnetic SF3OS06. To do so, we did a systematic calculation in GGA, GGA plus SOC, GGA plus SOC plus U scheme. The GGA, in the GGA scheme, it gives a metallic nature, crossing the Fermi energy, switching on SOC, it also gives metallic nature. However, it breaks into J is equal to 3 by 2 and J is equal to half states, and inclusion of Hubbard pole relation, there's a gap opening, and J is equal to 3 by 2 and lower Hubbard band, and J is equal to 3 by 2 upper Hubbard band. We get a gap in between these two. This dot structure is also represented in the band structure, and this is the schematic diagram for the effect of SOC and correlation here systematically. So we can say that SF3OS06 is a spin SOC entangled knot state in J by 3 by 2 sector. Here's the conclusion of the work, that is we get the monoclinic symmetry is the most preferred symmetry. However, the stabilization of SF3OS06, which is reported in cubic symmetry, is only due to the epitaxial growth of it on SRTI-O3 substrate, and ferromagnetic interaction is stabilized in cubic symmetry and supporting the large TC value, whereas antiferromagnetic interaction is supported in monoclinic structure with low transition temperature. And GGA plus SOC plus U scheme opens up a gap here. And our study also opens up a question for SF2COOS06, as it is expected to be a related double perovskite to support high TC like SF3OS06, as hopping parameter states and Borans factors are close to SF3OS06. Here is my references, and thank you all.
Thank you, Shreya, for the nice presentation. I see one question from Pratyay Ghosh. Yeah, you may please go ahead, Pratyay.
Thank you. Thank you for the nice talk. And I want to ask you one question that is it possible to somehow realize it from the lattice that your JH and your competition between the ferromagnetic and antiferromagnetic interactions are like physically understand it, not from the mathematics. So is it possible to see it from the distortions that you are showing?
From distortion in monoclinic structure, it is having a distortion which is structural. So in so antiferromagnetic interaction is being favored in monoclinic as the spin channels are open for antiferromagnetic is more favored over ferromagnetic channels.
Yeah, I exactly want to know that what does that? What allows the favoring and non-favoring thing?
The crystal symmetry plays a role whether it will be antiferromagnetic and ferromagnetic because so this is for QB what I have shown that T2G are degenerate, but for monoclinic, due to monoclinicity, these are split into 3 degenerate. So if we count the ferromagnetic and antiferromagnetic channel, for antiferromagnetic we are getting 4 channels, whereas for ferromagnetic we are getting only 2 channels between 2 osmium sites. So this actually supports.
Okay, yeah, thank you. Thank you.
Any other questions? It's open to everyone. Okay, I don't see any other questions. Then in that case, let's thank once again Shreya for the nice talk, and that's the end of the session. I think Manoranjan.
Okay, so
Yeah,
Seti,
please.
yeah, thank you very much for chairing the session.
Yeah, thank you
And
too.
it's the end of the today's all the sessions and today's like conference, and then we'll be meeting tomorrow 9:30. Okay, thank you very much.
9:30 a.m. right?
Of course.
Okay.
Okay. Okay.
Okay.
Thank you.
See you.
Bye.